Come to our next presenter, Catarina Baltazar from the University of Porto. Catarina is a researcher at the Faculty of Engineering at the University of Porto. And her research interests are in decision support systems and prognostics and health management techniques, especially in the area of Industry 4.0. And her talk today is about a prescriptive system for reconfigurable manufacturing systems considering variable demand and production rates.
So, hello everyone, my name is Catarina Baltazar, and today I'll be giving a presentation regarding our paper titled as Prescriptive Systems for Reconfigurable Manufacturing Systems Considering Variable Demand and Production Rates. So firstly, I'll briefly introduce our topics, followed by a concise literature review, and then I'll proceed by explaining our implementation. Once finished, the system validation results will be discussed, and lastly, some conclusions. So markets nowadays increasingly require customized products with shorter life cycles. So in response, the manufacturing systems evolve from mass production to mass customization, and they achieve that through flexibility in their production lines. And in order to achieve that, reconfigurable manufacturing systems arise to deal with uncertainty and individualized demand by combining both advantages of dedicated manufacturing lines and flexible manufacturing systems. So on one hand, we have the versatility of flexible manufacturing systems, and on the other, the high throughputs of dedicated manufacturing lines. So also during the current industrial revolution, there is an interest in the upgrade of prognostics and health management, as they allow improvements in reliability and the reduction of costs associated with maintenance actions. Also, a good prognostics and health management tool should be able to detect and predict failures in a timely manner, and this corresponds to the first two blocks, diagnosis and prognosis. And this information should also support decision making, which is the last block, and it is here where we insert our work. So our main goal is to develop a prescriptive system that recommends sequences of throughputs that will compensate production losses due to maintenance actions, and also will take into consideration the weekly production targets and the degradation of equipment. And since we are in a reconfigurable manufacturing system, the compensation for production losses can be achieved not only by tuning the different throughputs, but also by routing pieces to healthy assets. So when we refer to degradation of equipment, we need to take into consideration that different throughputs will impact equipment differently. So if we increase the throughput, the degradation will be faster, and if we decrease will decrease the degradation of equipment. So prescriptive systems can be understood as systems that recommend one or more courses of action, and there are prescriptive systems to help in the order of spare parts, scheduling, and life cycle optimization. And regarding their implementation, evolutionary and swarm algorithms are the most common ones. So before going into our implementation regarding the papers already published, I would like to highlight two where both optimize machine throughput using genetic algorithms, which will also be our approach. However, none of them take into consideration the possibility of routing pieces in order to compensate for production losses. So, taking into consideration our goal, we decided to implement a simulation-based optimization module. And this simulation will allow us to evaluate the solutions, what-if scenarios, and also simulate failure predictions. And our general approach is that the manufacturing system is running in the manufacturing environment simulation, and once a failure is detected, the optimization module triggered, and the generated solutions are evaluated through the simulation module, which is an image of the first block. And the optimization loop will occur until the termination criteria is met. And when it stops, the suggestions are presented to the operator. And now that I've given an overview of the implementation, the solution proposed, I will discuss each module individually by starting with the simulation one. In our paper, we simulated the systems as the ones in the figure. where a piece processed in any machine of the column, for example, 1 can go to any machine in the column 2. And this means that all machines in each column have the same available type of operations. And the pieces are processed sequentially. So they enter as input and get out output. And to model these kind of systems, we used graphs as they allow quick and easy changes in layout, offer good readability, and are easy to implement. Since we used graphs, a node corresponds to a machine and the edges, the connections between the machines, and these edges are weighted. The lesser the weight, the higher the priority, and this is how the machine knows where to send the piece. Also, each node has associated an object of the class machine, which saves several information regarding the equipment, and those informations can be divided into 3 types of parameters. The identifying parameters such as age and machine ID, however, not limited to these 2. Operation parameters, which is the types of operations available and the current throughput, and reliability related parameters such as mean time to repair and mean time between failures. These last type of parameters are very important because since we did not propose a predictive module, we need to somehow simulate the failures in order to validate our system. So we consider that the probabilities of failure are known and failure detection is done based on time intervals. So the mean time between failure associated with each machine decreases each tick of the simulation, and once it falls below a certain threshold, a failure is detected. And that threshold can be seen here as the time to failure, where in the current tick, the mean time between failure fell below a certain threshold. And the failure that once it falls below a certain threshold, failure is detected. And the failure detection can result into 2 different types of maintenances, the emergency maintenance or scheduled maintenance. And this depends if there is or not a maintenance shift schedule inside that time window. In the first case, since there is no maintenance shift associated, the failure will translate into an emergency maintenance, and this kind of maintenances always trigger the optimization module. However, in the second case, since we have a maintenance shift, the maintenance related to the failure F2 will start as soon as the maintenance shift starts too. And in this case, the optimization module is only triggered if the maintenance time is not enough to repair the equipment. And now that I went through all the main points of simulation, I'll start explaining the optimization one, which is the key to the prescriptive system, as it is what allows for the compensation in production losses. So the simulation module just exists in order to support the optimization one. And as I said initially, we chose to use genetic algorithms. And each solution is an individual, which is a chromosome, and each gene will represent the throughput of a certain machine at a certain day. So if you want the throughput of machine 1 at day 1, it is the first position. And here we have the fitness function, and where the first term is the difference between the production weekly targets and the number of pieces produced. In essence, it evaluates how far the system production is from the targets, and the square ensures the non-negativity of the values. The next 3 terms are all related to maintenance actions. The first one is the scheduled maintenance, the second, the emergency maintenance that I already explained previously, and the next one is regarding new maintenances in the following 3 days of the following week. So in order to prevent that we cause new failures due to the decisions that we are making in the current week. And also, since changing throughputs all the time is not practical, we introduced the last 2 terms in order to the algorithm prioritize more homogeneous solutions. So the first of these last 2 terms are the number of changes in throughputs, and the last one, the standard deviation of throughput per machine. So to wrap up, we have the manufacturing system in the manufacturing environment simulation running, and the failure that meets the requirements to trigger the optimization module occurs, and once it is called, it will generate solutions that will be evaluated through the simulation module until the termination criteria is met. And once it is, the suggestions are presented to the operator. In our case, the termination criteria is the maximum number of generations. And in our results, we always chose the suggestion with the best fitness value. So to validate the system, first we did some initial tests to assess the GA behavior, and then we went to more complex tests, which we will show the results in the next slides. And after several tests, the parameters that showed best performance were the ones presented in the slide, and we chose to use elitism, which means that a small portion of the best individuals are carried over to the next generation without changes, so to prevent the replacement of these good solutions during the next generation. And the metrics that we used to evaluate our results were the differential, which is the variation of pieces in relation to the production targets, and the availability of the system, which is defined by the ratio of total real operation time by the total theoretical operation time of all machines in the system. And we simulated during 1 week that we consider 5 working days. We tested several scenarios, several configurations, and each configuration into 2 different scenarios. One where the target is the same as the normal capacity of the system, and the other where the target is 20% higher. So in order to understand if the system can comply if the market demand increases. And when we say that we have a configuration 3x3, we have a configuration of 3 lines, 3 columns, so 9 machines in total. Here are the results. Each test was executed 3 times to understand if it was just luck or not. The results are the averages of those 3 runs and also the standard deviation of the differential. And the first table refers to the results to the first scenario where the target is the same as the normal capacity, and the second one where is 20% higher. And in all cases, the differential decreased, and in some cases, availability slightly increased, which are marked as green. And this example shows how the availability increased. And this is one specific run of test 4B, so configuration 10x10, where we produced an excess of 5 pieces. If we notice, the maintenances regarding the machines J5 and G7 disappeared from the current week, and the throughputs of those machines are in general lower than the baseline. So the algorithm decided to push these maintenances to the next week. And like this, the availability slightly increased. And this happens always in the configurations with more machines. So due to the higher redundancy of the system, the algorithm was able to achieve the target and push the maintenances to the next week. So to evaluate how the results vary from configuration to configuration, we plotted the averages of the differential, and when comparing the averages, we want that they gravitate towards 0 with low deviations, and the solutions seem to follow this behavior. However, as you can see, there is a slight increase in the deviation from configuration 3 to configuration 4. However, this increase didn't surpass the margin that we consider acceptable, which was 1%. And so it doesn't seem enough to jeopardize the results regarding the tested configurations, and can be attributed to the search strategy and convergence of the GA. However, we should do more tests, as we just did 3 tests per configuration. And that's one of the points that I will discuss in future work. So we presented a prescriptive system with an optimization module based on genetic algorithms allied with a graph-based simulation module, and the tested solution the results were consistent among all configurations. And further research should be conducted to surely generalize results, and it also very important to decrease processing times. And once we can decrease processing times, it will also be easier to do this generalization, if it is generalizable However, the indicators show that is. Also, this prescriptive system was developed with a future integration of a predictive module in mind, and that would be one of the first steps after taking care of processing times and in order to offer a more complete framework. So thank you for your attention.
Thank you very much for your presentation. Questions from the audience, please. Nobody? Then I would have one. So how do you see your approach related to, so like when I read about Industry 4.0 and smart factories, it's very often it's about, you know, predictive maintenance with classic standard machine learning algorithms like learning, training, and predicting. And how's this comparable with your approach? And do you think it's one can use each other, or it's contradictory, or what's the relation to such kind of?
I think they can be allied, and that is the point when I say that we want to integrate this optimization module with predictive one. So there are several works that use machine learning, deep learning to do the predictions of the failures, and then what we do with them. So in order to generate recommendations, we decided to use genetic algorithms. And now that we kind of validated our results, we integrated with those approaches that you were talking about.
Okay, thank you. Thanks again.
Thank you.